Module 10, Lecture A, Eval Exec, Compile. By the end of this lecture, you will be able to describe how eval, exec, and compile execute code strings and code objects within given namespaces. Use eval and exec in controlled examples that restrict available globals and locals to reduce risk. And identify scenarios where these built-ins should be avoided in favor of safer alternatives. Safe eval usage. Expression-only evaluation. When evaluating code safely, it is better to allow only expressions instead of full statements. Expressions simply compute and return values, like a formula or a function call, while statements can change program flow or modify data. By restricting user input to expressions, you greatly reduce side effects and prevent dangerous actions such as accessing files. This distinction between expressions and statements is essential for secure dynamic code evaluation. For example, when users provide a custom discount formula in an e-commerce system. Expression-only evaluation lets users customize behavior safely by allowing them to write formulas without full programming access. For example, analysts in a data dashboard can define calculated fields by combining metrics or applying math, and portfolio managers can specify risk formulas in financial tools. They can compute new values but cannot run loops, import modules, or connect to external systems. This keeps dynamic evaluation powerful while limiting it to safe value computations. Even when you restrict evaluation to expressions, it still runs in a controlled namespace that only exposes the names and objects you choose. This does not make it completely safe, but it makes behavior more predictable. You can decide which functions, constants, and data structures are available, and ensure they are side effect-free or tightly controlled. For instance, you might only allow certain math functions and fixed configuration values for tasks like computing insurance premiums or tax estimates. This way, the main result is just a value that your program can inspect, validate, or process before performing any irreversible actions. Python code. Expression-only evaluation. This section focuses on safely evaluating expressions using the evaluation function and contrasts this with the risks of executing full statements. It explains that expression-only evaluation can be controlled and limited, while executing arbitrary statements is unsafe and should be avoided. It also shows how to use a restricted namespace so that only specific, allowed values and functions are available during expression evaluation. Overall, a goal is to demonstrate how to perform controlled, secure evaluation of user-provided expressions. We begin by creating a safe namespace, which is a controlled dictionary that limits what can be accessed when we evaluate expressions. In this namespace, we disable built-in functions by replacing them with an empty dictionary, so potentially harmful operations cannot be used. We then add a single allowed value, a conversion factor from miles to kilometers, of about 1.60934. This setup lets us safely evaluate expressions that use this conversion without exposing any other functionality. The user provides a mathematical expression that computes a distance using only approved names and numbers. In this example, the expression multiplies 3 by the miles to kilometers conversion factor and then adds 5. By restricting the expression to this safe set of predefined variables and constants, the system ensures that only intended and secure calculations are performed. The program uses an evaluation function to compute the result of a user-provided mathematical expression that involves the miles to kilometers conversion value. This evaluation happens in a restricted environment where only specific, predefined variables and functions are allowed. Limiting what is accessible helps prevent the user from running unsafe or arbitrary code. The final computed value is then stored in a variable called result. We begin by showing the original mathematical expression, which converts miles to kilometers using a conversion factor. This expression is then evaluated safely in a restricted environment. After that, we display both the expression and its computed result. The result is rounded to 4 decimal places to keep it clear and precise. This process lets us confirm that the expression was evaluated correctly and makes it easy to compare the input with the output. This example defines a string that represents a potentially harmful command, which imports the operating system module and runs a system command that prints the word hacked. It shows how using the evaluation function on untrusted input can be dangerous. If misused, this function can run arbitrary code on the system. The key point is that evaluating user-provided strings as code creates serious security vulnerabilities and should be avoided. This explanation warns about a security risk when using the eval function. It points out that evaluating a string that tries to run system commands, such as importing the operating system module and executing a command, is dangerous. Instead of running this unsafe expression, the code blocks it and prints a message saying the expression is not evaluated. The main idea is to avoid executing arbitrary code with eval because doing so can create serious security vulnerabilities. This script shows how to safely evaluate mathematical expressions in Python by using the evaluation function within a tightly controlled environment. It only allows specific variables, such as a miles to kilometers conversion factor. So a user expression that multiplies 3 by this factor and adds 5 can be evaluated and printed along with its numeric result. The script also illustrates that using the evaluation function on unsafe input can be dangerous by presenting a harmful command, but it does not run this command. Overall, it emphasizes that evaluation should be restricted to trusted, well-defined expressions to avoid security risks. Controlled global namespaces. When using dynamic evaluation, it is important to tightly control what the evaluated code can see and use. Instead of giving it access to the entire program environment, you provide a custom dictionary that contains only the specific names you want it to work with. This creates a small, secure workspace where the code can interact only with approved functions, constants, and values. Anything not included is hidden, which helps prevent access to sensitive operations such as file handling or network features. This approach keeps even trusted expressions safely contained within clear boundaries. Controlling the global namespace is not only about blocking dangerous features, but also about making dynamic evaluation more predictable and understandable. By allowing only a small, defined set of names, You limit what evaluative expressions can do and tailor them to a specific context, such as math functions and read-only data in analytics or financial calculations in modeling. This focused set of accessible functions and data makes it much easier to audit or debug behavior because you can quickly see exactly what expressions are allowed to access without inspecting the entire program. In real systems, it is important to use controlled global namespaces to safely handle user-defined formulas and expressions. For example, a web dashboard can let users create custom alerts while preventing access to sensitive internal data by evaluating their expressions in a restricted environment. Educational tools can do something similar by exposing only safe, useful functions to learners. In this way, the global namespace becomes a clear, limited interface between the core application and any dynamic code, providing flexibility while maintaining security. Python code, controlled global namespaces. This section explains how to use the evaluation function with a restricted set of global names to improve safety. It contrasts using the full global namespace with using a carefully limited one, so you can clearly see the difference in what evaluated expressions are allowed to access. It also emphasizes that any names you do not include in the restricted globals remain completely unavailable and invisible inside the evaluated code. We define a helper function called miles to kilometers that takes a distance in miles and converts it to kilometers. Inside the function, we multiply the miles value by about 1.60934, since 1 mile is approximately that many kilometers. The function then returns the resulting distance in kilometers. Using this function, we can easily convert any distance from miles to kilometers by providing the miles value as input. We create a dictionary called full globals to control what is available when we evaluate expressions using the evaluation function. This dictionary makes a helper function for converting miles to kilometers accessible inside those expressions. It also exposes Python's built-in functions, such as the rounding function, through the built-ins module. By including both the helper function and the built-in functions, we provide a complete and controlled environment for safely evaluating expressions. We create a restricted global namespace by building a dictionary that contains only the helper function for converting miles to kilometers. This means that when we evaluate expressions, they can only use this specific helper function and nothing else. By limiting which functions are available, we control what parts of the code can run during evaluation. This approach improves security and helps prevent unintended access to other functions or variables. In this example, we use the eval function to run a piece of Python code that is stored as a string. We pass in a dictionary called full globals so eval has access to everything it needs. This dictionary includes the miles to kilometers function as well as Python's built-in functions. The expression converts 10 miles to kilometers, then uses the round function to keep only 2 decimal places. By including the built-in functions in full globals, we make sure round is available and the expression runs correctly. We evaluate an expression using restricted global variables so that only a helper function is available and built-in functions like the rounding function, are not. The expression tries to round the result of converting 10 miles to kilometers. But because the rounding function is missing, a name error occurs. This error is caught in a try except block, and instead of stopping the program, we save a message in the restricted result that explains a name error happened and includes the error details. This example shows code that evaluates an expression using a complete set of global variables. The expression converts miles to kilometers and then rounds the result. Because all the required built-in functions are available in the evaluation context, the expression runs successfully. This demonstrates how providing access to built-in functions allows such calculations to be executed correctly. This example shows what happens when code is run with a restricted set of global names. It evaluates an expression while only allowing access to a limited group of functions. Because the rounding function is not included in this restricted environment, trying to use it causes a name error. This contrasts with using the full global environment, where the rounding function is available and the expression would work normally. This example shows how the eval function in Python can be used with different global namespaces to control what code is allowed to access. A function is defined to convert miles to kilometers and then evaluated in two separate global contexts. In the first context, all built-in functions are available, so the expression that converts 10 miles and rounds the result works correctly. In the second, more restricted context, the round function is not available, so evaluating the same expression raises a name error. This demonstrates how limiting the global namespace when using eval can improve security and make the execution environment more predictable. Avoiding untrusted input. When using dynamic evaluation, never execute code that comes from untrusted sources, such as user input, network data, or external files. Anything outside your direct control should be treated strictly as data, not as code. Executing such input can let attackers manipulate your program, access sensitive information, or change its behavior in dangerous ways. Even well-intentioned users can accidentally cause serious errors if their input is run as code, so keeping this separation is essential for safety and security. You should never execute untrusted input as code, because it is extremely hard to reliably tell safe code from dangerous code inside a text string. Simple filters that look for certain words or characters are easy to bypass and can create a false sense of security. This means a web app that evaluates user input or a data analysis tool that runs user expressions with full access to the runtime can be tricked into exposing internal data or performing harmful file operations. The fundamental problem is that treating untrusted text as executable code removes the clear boundary between harmless input and powerful commands. To keep systems secure, always treat external input as data, not as code to be executed. Instead of running user-provided strings directly, provide a set of predefined operations or a controlled custom language that your system can interpret safely. For instance, users might build financial reports by selecting options from menus, or a scientific tool might translate expressions into a safe internal format that is processed step by step. This approach preserves flexibility for users while avoiding the dangers of executing arbitrary external code. Python code. avoiding untrusted input. Evaluating untrusted user input is dangerous because it can allow attackers to run arbitrary code instead of just performing a simple calculation. A naive calculator that directly feeds raw user input into a general evaluation function is unsafe, since any input is treated as executable instructions. To avoid this, a safer approach is to treat the input strictly as data. For example, by parsing it as numbers and allowed operations only, rather than executing it. This way, the calculator still processes user expressions, but does not give users the power to run unintended or harmful code. The script starts by importing Python's abstract syntax tree module, which lets the program work with the structured representation of Python code. It uses this module to safely parse and inspect user input expressions. By checking that only certain allowed operations and node types appear in the input, the script restricts evaluation to safe arithmetic expressions. This helps prevent the execution of harmful or unauthorized code. The code starts by setting a variable to a string that represents untrusted input, which is actually a command trying to import the operating system module and list the current directory. It then prints a message saying that an unsafe calculator is evaluating an expression from an untrusted source. This example is used to show how dangerous it can be to directly evaluate user input because it may run harmful commands on the system. This example shows code that uses the eval function to run a user's input as Python code, which is dangerous when the input is not trusted. The user's expression is crafted to list the contents of the current directory, illustrating a realistic security risk. The result of running this expression is stored and, if successful, printed to display the directory listing. If an error occurs, the code catches the exception and prints an error message. But this does not prevent unsafe operations from being attempted in the first place. This safer calculator is designed to accept only numeric values and basic arithmetic operators, which helps prevent the execution of harmful code. It clearly informs the user that any non-numeric or dangerous expression will be rejected. By limiting input to simple arithmetic, it ensures that only safe operations are processed, and untrusted input cannot be used to run malicious commands. The program safely evaluates a user's arithmetic expression by first parsing it into an abstract syntax tree in evaluation mode. It defines a small set of allowed node types, such as expressions, numbers, constants, and basic binary and unary operations. It then walks through every node in the tree and checks that each one is allowed, including only simple arithmetic like addition, subtraction, multiplication, and division. If any disallowed node appears, it raises an error and blocks the expression. Only if all checks pass does it compile and evaluate the expression in a restricted environment with no built-in functions. And any errors during this process are caught to ensure untrusted input cannot run unsafe code. This script shows why evaluating untrusted input in Python is dangerous and how to do it more safely. It first uses a simple approach that directly evaluates a user's expression, which can run arbitrary code such as listing files on the system, creating serious security risks. It then switches to a safer method that parses the input using the abstract syntax tree module and only allows numeric values and basic arithmetic. when the same harmful expression is tried again. This restricted approach blocks it and raises an error instead of running it. Overall, the example emphasizes the need to carefully validate and sanitize user input to avoid security vulnerabilities. Safe exec usage. Running code safely. When running code that comes from outside your program, always put safety first. Treat all external code as untrusted, even if it looks harmless or comes from someone you know. Restrict what this code can access and what actions it can perform, much like how operating systems and web browsers isolate different programs. This cautious approach reduces the risk of data leaks, crashes, and other security problems, and helps keep your system stable and protected. When running code dynamically, you must clearly define what it is allowed to do and what it must never do. For example, a small expression language in a financial dashboard should only perform arithmetic on predefined variables, not access files or the network. And a data analysis plugin should transform data without reaching sensitive settings. By exposing only the necessary elements and replacing risky capabilities with safe alternatives, you keep the code in a controlled environment. This turns broad, potentially dangerous powers into specific, auditable actions and greatly improves safety. When running code dynamically, you must think beyond correctness and consider performance, reliability, and auditability. Even harmless code can create infinite loops or use too much memory, causing outages or data problems. To manage these risks, monitor and log what the code does, limit how much it can affect system resources, and design your application to recover cleanly from failures. Capture outputs and errors, and structure the system so that one failure does not bring down the entire process. These safeguards help ensure dynamic code execution remains robust and supports your overall reliability goals. Controlling exec namespaces. When using dynamic code execution, it's important to tightly control what the executed code can access. Instead of exposing your entire program, you define specific dictionaries that act as the code's visible environment. These dictionaries list only the functions and data the code is allowed to use, such as selected math tools and the current dataset. By hiding everything else, you reduce the risk that user code can see or change private parts of your system. Managing namespaces is about controlling not only what code can access, but also what it can change. By giving each execution its own separate global dictionary, any new variables stay contained and cannot affect the main program. This isolation is especially important in long-running systems, such as web servers or educational platforms, where many code snippets run over time. It ensures one user's code does not interfere with another's and makes it easy to inspect or reset the state of each run. In educational settings, this allows students to execute code in clean, independent environments with no leftover state between runs. A carefully managed namespace limits which functions and data are available, helping control what code can do. You can make some values read-only with immutable objects and expose only selected helper functions, simplifying complex tasks while hiding unnecessary details. For example, in financial reporting, analysts might use custom formulas built on pre-computed data, but be blocked from importing modules or accessing files because those abilities are not included in the namespace. This setup is not a complete security solution, but it reduces unintended actions by exposing only what is necessary, so users can perform legitimate tasks more safely. Python code controlling exec namespaces. This section explains how to use the exec function safely by running it with controlled namespaces. It shows how providing a custom globals dictionary restricts which names are visible to the executed code. It also demonstrates that, when used this way, variables in the main program remain unchanged, keeping the rest of the program isolated from any side effects of exec. In this example, we create a piece of code that appears to perform risky actions. It first computes a new value called result by doubling an existing secret value. And then it tries to change a setting in the application to the word changed. The purpose of this setup is to show that when such code is executed inside a controlled environment, it can be prevented from altering important variables in the main program. We define two key values that must remain unchanged during code execution. The first is a secret value set to 100, representing sensitive data that external code must not modify. The second is an application setting initialized with the word original, which serves as a configuration value that should also stay fixed. By clearly establishing and protecting these values, we maintain the integrity of the main program even when other code runs. We create a special dictionary to control the environment where the code runs. This dictionary contains only the secret value from the main program, so the executed code can use that value but cannot see or change other variables. Any changes the executed code makes stay inside this dictionary, which protects the main program from unintended modifications. This code runs a piece of Python code using the exec function, but it does so inside a restricted environment defined by a dictionary called safe globals. By giving this dictionary to exec, the executed code can only use the variables and functions listed there and cannot see or change anything outside it. In the example, the code uses a variable named secret value that is safely provided in this dictionary. This setup keeps the main program's variables protected while still allowing controlled execution of dynamic code. The code prints the outcome of running code inside a restricted global environment. It calls the print function to show the message inside safe global's result, followed by the value stored under result in the controlled dictionary. This reveals what the executed code produced within that safe environment, without changing variables in the main program. This line outputs the current value of the variable from the main program to show that it has not been changed. It demonstrates that running the exec function with a restricted set of global values does not affect the original variable. As a result, the main program's data stays intact, which helps confirm the safety and integrity of the original values. The program prints the current value of a setting from the main code to show that it has not changed. This demonstrates that running code inside the restricted environment did not modify that setting. In other words, the main program's state stays the same, confirming that the execution function did not affect variables outside its controlled scope. This script shows how to safely run a piece of code using a controlled namespace, so it cannot interfere with the main program. The main program has a secret value and an application setting, while the code snippet tries to change a variable and create a new one. The code is executed with a restricted set of global values that only includes the secret, so it can compute a result based on that secret and store it in the restricted dictionary. However, it cannot modify the original secret or the application setting in the main program. This demonstrates how a controlled namespace isolates executed code and protects the main program's variables. Managing global side effects. Running dynamically supplied code can be risky because it may change the global state of a program, such as configurations or shared functions that other parts of the system rely on. When code executes in a shared global namespace, it can unexpectedly overwrite important values or behavior, which makes debugging and maintaining the system much harder. For example, a user script on a data analysis platform could replace critical functions or constants and cause inconsistent results later. To avoid these problems, it is important to treat the global namespace as a shared resource and carefully control what dynamic code is allowed to access and modify. To control global side effects when running dynamic code, execute it in a separate restricted environment instead of giving it access to your program's real global variables. Provide only a limited set of allowed names, such as selected math functions or helper tools. So this sandbox contains everything the code needs, but nothing more. Any changes the dynamic code makes then stay inside the sandbox and do not affect the rest of the application. For example, a learning platform can safely let students experiment in such a curated environment without risking its core functions or other users' work. Even if you isolate the main global namespace, code can still cause indirect side effects through the objects and services it can reach. If the environment exposes databases or network clients, scripts may still change real systems, such as writing to production data. To reduce this risk, carefully limit which objects are exposed. Prefer read-only or mock interfaces, and encapsulate sensitive operations. By combining namespace isolation with strict control over exposed objects, you can greatly reduce unintended changes to global state or external dependencies. Python code: managing global side effects. This material explains that using the exec function can be dangerous because it can directly modify global variables in unexpected ways. It then shows that running exec with a restricted or sandboxed set of global variables can block these unwanted changes to the real global state. Finally, it demonstrates a safer pattern where exec is given its own isolated global environment, so any side effects stay contained and do not affect the rest of the program. The program begins by setting up a configuration structure that stores settings such as a 7% tax rate and the use of US dollars as the currency. It also creates an empty collection intended to hold log messages produced while the program runs. These two pieces of shared data are introduced to illustrate how global state can be created and modified throughout the code. The code starts by printing the current values of two global variables that hold configuration settings and log messages. This shows their state before any risky or unsafe operations are run. The configuration variable is a dictionary with settings such as tax rate and currency, and the log variable is a list used to store messages. By displaying them first, the code establishes a clear baseline so any later changes caused by the executed code can be detected and compared. In this example, a string contains Python code that changes a tax rate, updates a configuration dictionary, and adds a message to a log list. The exec function is then used to run this string as actual Python code. Because exec is given access to the global and local variables, the code inside the string can directly modify them. This shows that using exec can unintentionally change global state and must be used with great care. After running the unsafe code, the program shows the current contents of the real configuration dictionary, revealing that this global value has been changed by the executed code. It then displays the actual list of log messages, which now contains an extra entry. Together, these outputs illustrate that using an execution function with access to global variables can directly modify shared data, creating significant risks for the program's integrity and security. We create a separate dictionary to act as a sandbox environment with its own configuration and log list, so that any changes do not affect the real global variables. In this sandbox, the configuration starts with a 7% tax rate and currency set to US dollars, and the log list is empty. We then define a string that contains Python code to be executed later inside this sandbox. That code sets a local tax rate of 30%, updates the sandbox configuration to use this new rate, and records a message about the change in the sandbox log. This way, all modifications stay isolated within the sandbox environment. This code runs a block of Python using the exec function, but it places all variables in a separate dictionary that acts as a sandbox. Any changes the code makes affect only the sandboxed set of variables, not the real global variables of the main program. By isolating the execution environment in this way, it helps avoid unintended side effects and keeps the main program's global state unchanged. After running the sandboxed code, we print the real configuration dictionary and see that it has not changed, which shows that the sandbox did not modify the global state. We also check the real list of log messages and confirm that it is unchanged as well. Together, these checks demonstrate that using a separate dictionary for the global environment in the execution function prevents unintended side effects on the actual global variables. The code prints the contents of the sandbox's global variables, showing the configuration data and log messages that were changed during the sandboxed execution. This output confirms that any modifications made by the executed code are confined to the sandbox environment. As a result, the original global variables in the main program remain unchanged. This illustrates a safer way to run dynamic code without causing unintended side effects on the main program's state. This material explains why using the exec function can be dangerous when it is allowed to modify global variables and how to reduce that risk. In the unsafe version, exec directly changes a shared configuration and adds a log entry, showing how it can create unintended side effects on global data. In the safer version, exec runs in its own separate dictionary that acts like a fake global environment, so the real configuration and logs are not touched. After running the sandboxed version, only the isolated environment is modified, while the actual global variables stay the same. This demonstrates that isolating exec in a sandbox is a safer way to control its side effects. Safe use of compile. Compiling code safely. Treat any source text you pass to the compile function as potentially unsafe unless you fully trust and control it. Although compile itself does not run code, it is often followed by functions that do execute the result, so a bad choice here can lead to serious security problems. Avoid compiling code from untrusted places, such as user input or external files, especially in web applications. Instead, prefer safer approaches like restricted languages or parsers that limit what Python can do. Use compile only when you have strong reasons to do so and complete control over the code and its entire lifecycle. When using the compile function, you must decide carefully where the resulting code will run and what it can access. The compiled code is often executed with evaluation or execution functions, and the namespaces you provide determine its abilities. If the code should only perform simple arithmetic, run it in a restricted environment without access to files or network features. In data analysis, you might compile expressions that work only with a dataset and a few helper functions. By defining this execution context in advance, you reduce the risk of the code being misused or extended in unsafe ways. To safely use a compile function, you should first restrict and validate the code structure, instead of relying on it as a security sandbox. You can inspect the text or its syntax tree and only allow simple, predefined patterns, such as basic arithmetic and a few math functions, while blocking things like attribute access, function definitions, loops, and imports. This does not make running arbitrary code safe, but it lets you treat the input as a limited configuration-style language. Combined with careful control of the variables and functions available when the code runs, this approach makes compilation more predictable and reduces security risks. Python code, compiling code safely. We will show how to compile only safe expressions that use a restricted set of allowed variables, and how to block anything that tries to access disallowed data or operations. Unsafe expressions are detected and rejected before the compilation step, so they never run at all. Finally, we emphasize that any compiled expression executes inside a tightly controlled, limited namespace designed to keep the environment safe. The code starts by importing the Abstract Syntax Tree, or AST, module, which lets Python code be parsed into a tree that represents its structure. Using this tree, the script can analyze and manipulate code programmatically. This is important for checking whether expressions are safe before compiling and running them. By relying on AST, the script can allow only approved operations and block potentially harmful code from executing. We define a restricted set of allowed node types using the Abstract Syntax Tree module, including expressions, binary and unary operations, numeric values, variable names, and the load context. This limited set ensures that only very simple arithmetic expressions can be processed. By allowing only these specific nodes, we block more complex or potentially dangerous code. This approach helps maintain a secure environment when evaluating expressions provided by users. We define a limited set of arithmetic operators, including addition, subtraction, multiplication, division, exponentiation, and unary minus. By allowing only these basic operations, we tightly control what kinds of expressions can be evaluated. This restriction helps keep the evaluation process safe and prevents the execution of any potentially harmful code. This function checks whether an expression is safe to compile by analyzing its structure. It first tries to parse the expression into an abstract syntax tree in evaluation mode, using the language's syntax tools. If this parsing step fails with a syntax error, the function immediately returns false. This means only expressions that are syntactically correct move on to any further safety checks. The code walks through each node in the abstract syntax tree of an expression and checks whether it belongs to a set of allowed node types or operators. If it finds any node that is not in this allowed set, it immediately returns false, meaning the expression is considered unsafe. If it finishes checking all nodes without finding a problem, it returns true, indicating the expression is safe to use for further processing. We create a restricted namespace by setting up a dictionary of allowed global values that is empty except for a special built-ins entry, which we also set to an empty dictionary. This removes access to Python's usual built-in functions and variables. As a result, any expressions we evaluate later run in a tightly controlled environment and can only use the specific variables and functions we choose to provide, which helps prevent unsafe operations. We create a dictionary called a safe local namespace to hold the values used when evaluating expressions. In this example, it stores two numbers, miles set to 10 and hours set to 2. These values can then be used in arithmetic expressions during evaluation. By limiting access to only the data in this dictionary, we restrict what the evaluation can use and help prevent unintended or malicious code from running. We define a list of expressions that users might enter, starting with a simple calculation of miles divided by hours. A second expression combines miles squared with hours multiplied by 3 to show a slightly more complex arithmetic operation. A third expression tries to import the operating system module and run a system command, which is unsafe. This last example is included to illustrate how the code should detect and handle potentially harmful operations. We go through each user expression in the list and announce that we are trying to evaluate it. For every expression, we call a function that checks whether its structure is safe. If the expression is not considered safe, we report that it has been rejected because its structure is not allowed. We then print a separator line and move on to the next expression. So only safe expressions continue to later processing steps. The code takes the user's input expression and compiles it into a form that can be evaluated later. It calls a compile function with the expression and uses a placeholder name to show that the source is user input, not a real file. The compile mode is set so the input is treated as a single expression rather than a full program. This setup makes it possible to evaluate the expression later in a controlled and safer environment. The code uses the evaluation function to run a compiled expression inside a restricted environment. It relies on predefined global and local settings that limit what the expression can access. In this setup, only specific variables are available and built-in functions are blocked. This controlled execution helps maintain security by preventing unauthorized or harmful operations. The code evaluates a user-provided expression that has already been checked for safety, then prints a message showing the phrase safe result value, followed by the actual result. This confirms that the expression ran correctly and without security issues. After displaying the result, it prints a line of dashes to visually separate this output from others. This makes it easier to distinguish and read the results of multiple safe expression evaluations. This script shows how to safely compile and evaluate arithmetic expressions in Python using the abstract syntax tree. It defines which kinds of syntax nodes and operators are allowed, focusing only on basic arithmetic. Each user expression is checked against these rules, and anything unsafe, such as trying to import a module, is rejected before it can be compiled. Expressions that pass the checks are then compiled and evaluated in a restricted environment that only contains predefined numeric values. As a result, valid arithmetic expressions are computed correctly, while unsafe attempts are blocked to ensure secure execution. Compile Modes Overview. When using the compile function in Python, choosing the correct mode is important because it defines what kind of code the string represents and how it will run. The main options are expression mode, single statement mode, and file or script mode, and each reflects a different intent and level of safety. Expression mode is used for a single expression that produces a value, such as a formula, and it does not allow statements like assignments or imports. This restriction makes expression mode safer, since it limits the ability to perform arbitrary actions unless they are explicitly permitted. Single statement mode is a flexible way to run code one line at a time, often used in interactive tools where users can enter expressions or full statements. It supports assignments, imports, and function definitions, so it can change program state and create new variables. Because it can perform almost any action that normal Python code can, it becomes risky when handling untrusted input in environments like web consoles or educational sandboxes. This power makes it potentially dangerous, so it should be avoided unless there are strong security protections and a clear reason to use it. File or script mode compiles Python code as if it were a complete file, so it can run initialization code, define many components, and execute top-level logic in one step. This makes it very flexible and suitable for handling full modules or complex scripts. However, it is also the riskiest option for untrusted input, because it allows extensive actions that are hard to control. For this reason, it should be reserved for trusted sources such as internal scripts, and avoided for user-generated content in networked or automated systems, where safer compilation modes are preferable. Python Code Compile Modes Overview. Different compile modes control what kind of code is allowed and what safety expectations you should have. Expression mode only lets you compile a single expression, which is relatively constrained and easier to reason about. Single statement mode allows one full statement, giving a bit more power and complexity. Full script mode accepts an entire program, enabling the broadest range of behavior. As you move from expressions to single statements to full scripts, the potential impact of untrusted code grows, so the security risks and need for careful isolation increase. We create a string that represents a simple math expression, 3 times the sum of 5 and 2. Then compile it using Python's compile function in expression mode to prepare it for evaluation. Next, we evaluate this compiled expression with the eval function while passing an empty built-ins dictionary to limit access to built-in functions for security. Finally, we print the numerical result of the expression, showing that in expression mode, we only obtain the value that the expression produces. We create a short Python program as a text string that sets a variable to 10 and prints its value. This string is then turned into a code object using the compile function in single statement mode, which is suitable for running one interactive statement. We set up a restricted global environment as a dictionary that only allows access to the print function from the built-in functions. Finally, we run the compiled code with the exec function inside this controlled environment, which executes the program and prints the value of the variable. We create a text string that holds a short script which multiplies 12 by 3 and prints the result. This text is then compiled in execution mode so it can run multiple statements, and we give it a file name to use in any error messages. We prepare a dictionary of global variables that only exposes the print function from the built-in features for safety. Finally, we run the compiled script with the execute function and this restricted global dictionary, which performs the calculation and prints the answer. This script shows how Python's different compile modes change what code can do and how safe it is. It compares expression mode, which only evaluates a simple calculation, with single statement mode, which can run one line that assigns and prints a value, and full script mode, which can run a small program that computes and prints a total. The examples produce results like 7, 10, and 36, but the key idea is that each mode allows a different level of complexity. Because broader modes can perform more powerful operations, they also carry greater risk when running untrusted code. Reusing compiled objects. When you need to run code dynamically and have already validated the input, compiling the code once and reusing the compiled result can improve both safety and performance. You create the compiled code object under strict, controlled conditions, then repeatedly execute that trusted object with different data. For example, a data analysis tool can compile a user's expression a single time, store it, and then apply it to many data sets. This centralizes and simplifies auditing and testing of the compilation step, while later executions just plug new values into the same stable code structure. Reusing compiled code objects lets you keep code definitions separate from when they are actually run, which is important for safely handling dynamic features. In a web app that uses a special language for business rules, trusted staff can write rules that are compiled, checked, and stored securely in advance. Later, when users trigger workflows, the app runs these pre-compiled, validated objects instead of compiling whatever input the user provides. This ensures that only vetted code is executed and avoids the security risks of compiling potentially harmful input on each request. Reusing compiled objects is important not only for performance, but also for security and control in sensitive systems. In a financial risk engine, for example, analysts define pricing formulas that are compiled once in a controlled deployment process, carefully reviewed, and then reused many times. This approach ensures the code is safe, reduces the chance of injection attacks, and limits the need to introduce new dynamic code. As a result, testing and monitoring becomes simpler because you only need to manage a small, trusted set of compiled components instead of constantly evaluating new, potentially unsafe code. Python code. Reusing compiled objects. Compile the expression once, then safely reuse that compiled version for many evaluations. Show that different data rows can all pass through the same precompiled transformation instead of recompiling each time. Emphasize that the transformation logic is trusted code, while only the input values change, keeping a clear separation between stable, verified behavior and varying data. We define a trusted expression that converts a measurement from inches to centimeters by taking a value in inches and multiplying it by 2.54, the standard conversion factor. This expression is stored as a reusable string, so it can be compiled once and applied repeatedly. Doing this ensures that all conversions are consistent and efficient whenever we need to change inches to centimeters. We first create a trusted expression that converts inches to centimeters by compiling it once in evaluation mode. This produces a compiled expression object that represents the conversion logic. We can then reuse this object for many different input values, applying the same conversion each time. This avoids recompiling the expression repeatedly and makes the conversion more efficient. The code sets up a list of board lengths in inches using the values 8, 12, 20, and 36. This list acts as the input data for a later step in the script. In that step, each length is converted from inches to centimeters using a precompiled conversion expression. By organizing the measurements in a single list, the same conversion can be applied consistently to all of them. We loop through each board length in inches and apply the same precompiled conversion expression to it. This lets us reuse the compiled code efficiently instead of recalculating the conversion each time. As a result, every board length is processed in a consistent way when converting from inches to centimeters. We create a dictionary to store the local variables for the current board length. In this dictionary, the key called value in inches is linked to the current length in inches taken from our list. This structure lets us safely provide the current board length as input to the precompiled conversion expression. In other words, the dictionary acts as a controlled way to pass the length value into the conversion step. The code uses a precompiled expression to convert inches to centimeters by evaluating it with the eval function. It passes an empty set of global variables, so nothing from the outside can affect the calculation. It then supplies a local set of variables that includes the current board length in inches. With this setup, the expression safely computes the corresponding length in centimeters for each board. The program prints a short summary for each board length, showing the original measurement in inches and its converted value in centimeters. It uses formatted text to present this information clearly. The centimeter value is rounded to 2 decimal places, so the output is easy to read and interpret. This script shows how to reuse a compiled expression to convert lengths from inches to centimeters efficiently. It first defines a trusted conversion formula and compiles it once into an expression object. That same object is then used to evaluate each board length by supplying only the current length as input. For every value, the script prints the original length in inches and its converted length in centimeters, rounded to 2 decimal places. This method separates trusted code from changing input, improving both performance and security by avoiding repeated compilation. In this lecture, you learned to describe how Eval, Exec, and compile execute code strings and code objects within given namespaces. Use Eval and Exec in controlled examples that restrict available globals and locals to reduce risk. And identify scenarios where these built-ins should be avoided in favor of safer alternatives. In the next lecture, Lecture B, we will go over slices hash format.
Thank you for your attention. See you all in the next lecture.